All right, guys, how's it going? Today, I'm going to go through and talk about Lewis diagrams, how to draw Lewis structures. How do you go through and take a covalent molecule like CO2, carbon dioxide, and turn that into a 2D representation. That's basically all this is, just basically how to draw a Lewis structure. So before we do Lewis structures, we have to kind of remember our electron dot structures. This is something that you probably have picked up in pre-AP, but if not, let's just run through it again real quick. So for the electron dot structure, what you initially do is just write down the chemical symbol. For sodium, it'll just be Na. Right? Now, this is going to be for the atom sodium, not the ion sodium. So with sodium, what you do is think about how many valence electrons it's going to have. Well, sodium is a group 1 element, so it's going to have 1. So I'm going to add 1 valence electron to it. So that is going to be its electron dot structure. Pretty simple. Now, if I wanted to do sodium, the ion, well, it lost that electron, didn't it? So this, just sodium without any electrons around it, would be the electron dot structure for sodium, the sodium ion. Now let's look at chlorine real quick. We'll do the opposite of it. So chlorine by itself is going to have 7 electrons. It's group 17. It's a halogen. So it's going to have 1, 2, 3, 4, 5, 6, 7 electrons around it. Now, you may have noticed that I went through and I added them in kind of a specific order. What I did was placed 1, and then I moved to the side, placed another one, moved to the side, the bottom, placed another one, over here, placed 1, and then I started pairing them up. This is kind of what you do whenever you're doing electron configurations, right? The electrons want to stay apart and live in their own apartment, live in their own orbital first, and then they only pair up whenever they have no other place to go. So that's kind of what we're doing here. We're adding them in, and we're not pairing them up until there's no other spot, up, down, left, right, for them to go. That's how we go about doing that. Now, what about the ion? What about a chloride minus ion? So how would that work with the chloride ion? The chloride ion, you would go through, it would be the same, but we just added 1 more. So 1, 2, 3, 4, 5, 6, 7, 8. Now it has that full octet that it was looking for before. Now let's go through and look at some of these covalent non-metal compounds. So for oxygen, you would look and you would see that oxygen would have 6 valence electrons. So you would say 1, 2, 3, 4, 5, 6. Now this tells you a couple of things that's interesting about oxygen. Oxygen is going to have 2 of these single electrons hanging out. This kind of lets you know that oxygen is probably going to have 2 bonds associated with it. It's either going to have 2 single bonds or 1 double bond. Then for carbon here, it has 4 valence electrons, so 1, 2, 3, 4. It has 4 single electrons, so it's probably going to have 4 bonds associated with it. So this is going to be one way for you to go through and remember when you're drawing your Lewis structures, how many bonds each of these guys should have. I'm going to go through now, and I'm just going to go give you a step-by-step guide to drawing Lewis structures. If you follow these steps, you'll get the correct Lewis structure 98% of the time. There's going to be some weird exceptions that I'll talk about later on, in particular with the resonance structures, formal charges, and some of these weird exceptions. But this is going to be your basic procedure to go through and draw a Lewis structure. So first, figure out the number of atoms and the types of atoms. Well, we have 1 carbon, 2 hydrogens, and 1 oxygen. Then we're going to write out the dot structures for these guys. Carbon has 4 valence, so 1, 2, 3, 4. Right, already I know that carbon is probably going to have 4 bonds. Hydrogen here has a electron, 1 electron. So that's going to, he's probably going to only have 1 bond. And then oxygen here is going to have 1, 2, 3, 4, 5, 6. It's going to have 2 bonds associated with it. Drawing out the dot structures like this can help you go through and remind yourself, carbon's probably going to have 4, hydrogen's going to have 1, Oxygen's going to have 2 bonds associated with it. This is going to be helpful whenever you're actually kind of arranging them. There's going to be some rules for arranging these atoms, but you can kind of already see carbon is probably going to be in the center because it has 4 little connection points. Hydrogen is always going to be on the outside because it's going to have a connection point. And oxygen is probably going to be somewhere in the middle. Next step, determine the total valence shell electrons. How many total electrons are there going to be? So for carbon, we know there was going to be 4. We have 2 hydrogens at 1 apiece. So hydrogen is going to give 2. And then oxygen here is going to give 6. So if we sum these together, we're going to get a total of 12 electrons. Fantastic. So we know that there's going to be 12 electrons. The little E minus here is how I write down electrons. So 12 electrons in this molecule. There's not going to be any more. There's not going to be any less. We know there's going to be 12. That's how many we have to play around with. Now we're going to go through and arrange the atoms and add some bonds because we know there's going to be at least 1 bond between everything that's arranged. Now here are some basic rules for you to remember here, that hydrogen is always going to be on the outside. It only has 1 bond that can associate with it, so it's always going to be on the outside. The electronegative atoms are going to be on the outside. Atoms that are on the outside of a molecule are not going to share their electrons as much as the ones in the middle. If you have some in the middle, they're going to share their electrons with everyone that they're connected with. Oxygen is very electronegative. Remember, it's on the top right. So that electronegative property of oxygen is going to mean that it's not really going to want to share as many of its electrons. It's going to be on the outside of the molecule. So if I wanted to go through, I know that carbon is probably going to be in the center. It's the least electronegative, so it's going to be my central atom. Then I know that oxygen is going to be on the outside as well. And then hydrogen and hydrogen are going to be on the outside as well. So this is going to be our basic setup. We know that there's going to be at least 1 bond. So I'm going to draw my bonds in red. So there's going to be 1 bond here, 1 here, and 1 here. We know that this carbon is bonded to all 3 of these atoms, 2 hydrogens and oxygen. So how many electrons did I just use right there? Well, each bond is 2 electrons. So this is going to be 1, 2, 3, 4, 5, 6. So I have a total of 6 electrons that I used. Remember, I started with 12, and I'm taking away 6, so I have 6 electrons left that I can play around with. The next step is going to be to add all the unshared electrons. Now I have 6 electrons left, and I'm going to be giving out these electrons to try to get everyone to an octet. I want to have every atom have an octet, except for hydrogen. Their octet is more of a duet with 2. So we're going to fill the valence electrons of the outside atoms first. This is going to be your most electronegative atoms. They're the hungriest. They're the ones that are going to be, if I'm handing out cookies to kids, the hungry kids are going to be up front. The kids that aren't that hungry are going to, be in the back of the line. So the first person in line is going to be the most electronegative, the oxygen. And I'm going to start giving oxygen more electrons. So 1, 2, 3, 4, 5, 6. Now I have given him 6 electrons, and he is at this full octet. So I'm taking away 6, and I'm now out of electrons. I have no more electrons to give. So since I have no more electrons to give, I can't add any more. Now we're going to move on to the next step. The next step is to check for octets. We need to make sure that every atom has an octet. Let's go through and check hydrogen here. This hydrogen has a full octet. It has 2 electrons, so it's completely fine. This hydrogen here, again, has a full octet, or it has 2 electrons. It's completely full, so it's fine. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. It's fine. It has an octet. But if we look at this guy, the carbon here, it has 1, 2, 3, 4, 5, 6. It's missing its octet. It does not have enough electrons around. So we know that there's going to be something that we're going to have to do for that. And what we do is we move lone pairs from something that's connected to the electron deficient atom to make it have an octet by sharing a little bit more. Kind of think of it like this. We have the kid with the really hungry kid coming in, bursting to the front and grabbing all the cookies, and we realize someone doesn't have enough cookies that was in the back of the line. This is whenever the parent has to step in and say, okay, Jimmy, give Krista 2 cookies because you have 8 and she has 3. So what we're going to do is move those 2 electrons, valence electrons, and make them into a bond. So now we have a double bond between this carbon and oxygen. This oxygen still has 8 electrons, and this carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So now that carbon's happy. These are some exceptions where the atom doesn't actually follow the octet rule. Kind of like hydrogen. Hydrogen is happy with 2. That makes sense. It only has a 1s orbital. But others, like boron, for example, boron's one of the big ones. Boron is happy to exist with 6. Boron is completely happy with 6 valence electrons. Let me kind of show you how this works in practice. So one of the things that you will always see in an exam is boron trifluoride. Boron trifluoride is used quite often because boron is one of these exceptions to the rule. So you're going to do the same thing as before. Boron, you know, is going to have 1, 2, 3, 3 valence electrons. And fluorine is going to have 7, but there's 3 of them, so 21. That's going to mean that we have 24 electrons that we're going to be divvying out to this. Boron is less electronegative than carbon, so it's going to be in the center. And then you're going to have fluorine on the outside, kind of arranged evenly across. These guys are all going to have a bond. So I used 1, 2, 3, 4, 5, 6. I'm now down to 18 electrons. And then I'm going to go through and add in electrons to the most electronegative atoms first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And I ran out of electrons. Now you see here that boron is electron deficient. It does not have its full octet. But because it's one of these exceptions, boron actually is okay with that. It's perfectly fine with 6. Another exception is anything that has d orbitals in it. If I go back to look at the periodic table, anything that's in period 3 or lower, it's going to have access to these d orbitals. Remember that period 3 is that 3rd energy level, so there are going to be 3d orbitals available. So those orbitals, 3d orbitals, are going to be available for electrons to jump into, which means that things like sulfur, phosphorus, iodine are going to be able to have more than 8 electrons. See this in action. So let's say I'm going to be looking at sulfur sulfur hexafluoride. Sulfur hexafluoride, you can go through and do the same thing as before. I'm going to have 1 sulfur. Sulfur is going to have 6 electrons, and then I'm going to have 7 electrons from fluorine, but there's 6 of them. So 7 times 6 is 42. And then we're going to go through and say 48 electrons. So we have 48 electrons. Now sulfur is going to be in the middle because it's the least electronegative, and fluorine is going to be arranged around it evenly. And you know there's going to be one bond between sulfur and each of the fluorines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I used up 12 of these guys, so I have 36 left. And then I go through and I start adding electrons in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. 36, we're down to 0. If you look here at octets, the fluorines are all happy. They all have an octet. But sulfur here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. 2 more electrons than it had before. How can it possibly have that? Well, remember, it's because sulfur has access to these 3d orbitals, which means it is that extra 2 electrons can exist in these d orbitals. So anything, if you ever see a central atom that is in the 3rd period, especially anything over here, the nonmetals and lower, then start thinking, ooh, maybe there's going to be some d orbital shenanigans going on. One other thing that I want to talk about is this definition of isomers. What is an isomer? An isomer is going to be the same chemical formula, but the structure is different. So you see here you have butane, you have C4H10, but if you change up the Lewis structure a little bit, you can get this configuration, this isomer of butane. We call this one isobutane and this one butane. So just be aware of that term isomer. Isomer just means it's the same chemical formula, but it has a different Lewis structure. That's it for this video. Hope you guys had a good day, and I will see you later.